Welcome back. In this lecture, as a part of EE 5110, we will look at the axiomatic theory of probability. So, I will be using the lecture notes that has been prepared during the last year's run of the course EE 5110 along with some more extra slides. First, we will look at the lecture notes. So let's recollect the various definitions associated with the random experiment. So a random experiment or a trial is an experiment in which the outcomes are not predictable in nature, but we can list out all possible so-called elementary outcomes, also called as the sample points of that random experiment. We denote it, the sample points, using the notation omega. So omega 1, omega 2, etc. are all the sample points of the random experiment. The set of all elementary outcomes or the sample point constitute the sample space. That is, the set omega I constitute the sample space, and it is usually denoted using two symbols, the capital omega or the S written in this form. So these are two notations used to denote the sample space. We also saw that there are certain things called events which is of interest to us. So we are basically interested in constructing a theory of associating probability, which is a measure of likelihood of occurrence of those events. So events are the one which is of interest to us. So when we conduct a random experiment, we just look for whether an event has occurred or not. So an event is nothing but a subset of the sample space. So every event E subscript I is a subset of omega. Then there may be many events that on which we are interested in, and later we will define a probability measure for each those events, and for each such event we will define or come up with the probability measure. But we would like to have a structure on the class of events on which we want to define the probability measure. So this class of events F should have some structure, and what we look for are the following. First thing is that the entire sample space should be an event for which we should be able to assign the probability measure. So the sample space omega itself should be an element of this class. We will call this class of events as the sigma algebra. Then if there are two events E1 and E2 which are element of the sigma algebra F, we expect that their union to also be present under the sigma algebra. That is, the set union operation, the sigma algebra is closed under the set union operation. Then if E is an element, is an event, then its complement, denoted as E1 complement, should also be an element of F, which means that basically sigma algebra is a class of events that is closed under the operation of finite number of set union operations and set complementation operations, and also has the sample space in it. Later we will see that these two conditions will also make the sigma algebra to be closed under the set intersection operation. Then we looked at that the Venn diagram is a good way of dealing with the various set related operations, which will be very much helpful in our course of defining a probability measure on that. So we have defined so far two things. One is the sample space, and then a sigma algebra defined over the sample space. The next thing what we want to do is to associate to each event a notion called the likelihood of the occurrence of the event. That is, we want to associate a measure that in some sense tells you how likely the event is going to happen. So we will come to the problem of defining an valid probability measure on the events present in the sigma algebra. The first thing that we can easily come up is the sample space is nothing but a sure event, because when we conduct an experiment, one of the various outcomes associated with the random experiment has to occur, which means that if you define the sample space itself as an event, that event will definitely occur, or it is a sure event. So the likelihood of it occurring, the sample space occurring, should be the maximum one. So it should have a maximum likelihood of occurrence. Similarly, if you look at a empty set, that will corresponds to an impossible event because it has no sample points. But if you conduct a random experiment, a sample point should occur, which means the null set cannot occur. So therefore it is an impossible event, and therefore the likelihood of it occurring has to be the least value. Okay, so we can now tell that the probability measure should be such that sure event or the sample points has the maximum value and the impossible should have the minimum value, and for any other event, say E, its probability measure should lie in between these two range values. So the range of values that can be taken by the probability measure for E should lie between the value taken by the sure event and the impossible event. So therefore we can fix two values for the sample space as the probability measure for the sample space and the impossible event. One possible value that we can take is the probability of the impossible event to occur to be 0 and the probability of occurrence of the sure event to be 100, and let the P of E take a value between these two. That is one way in which we could have defined. But rather, as a convention, what we do is we take the two limits to be 0 and 1. So with this we will start defining or introducing certain axioms based on which we will construct the probability theory. So we set the probability of occurrence of the sample space to be 1, which is the maximum value it can take, and the probability of occurrence of the impossible event to be 0, and therefore the probability of occurrence of any given event E should lie in between 0 and 1. Now it can also be seen that empty set is nothing but a complement of the sample space, and later using one axiom we can see that the probability of this can also be arrived at using another axiom. Okay, that probability of occurrence of the impossible event is 1 minus the probability of occurrence of the sample space, and therefore it is 0. Okay, the next one, as I mentioned, the measure for the probability of occurrence of any given event should lie within this range. Okay, so therefore we say let P of E to lie between 0 and 1. Okay, that simply follows because psi actually this is a less than or equal to operation, whereas this is a subset operation. So psi is a subset of E, and E itself is a subset of omega, and therefore because of this one we get that the probability measure should lie within this range. Okay, then we go about introducing one more axiom to this, that we call it as the additivity property. Let us assume a sample space omega in which there are two events A and B, such that this A and B are disjoint events, that is A intersection B is equal to a null set. So there is a likelihood of occurrence of the event A, similarly another likelihood of occurrence of event B. So if we conduct an experiment and ask a question, what is the probability of occurrence of either A or B, then we expect that the sample points that either lie in A or those which lie in B will contribute to the probability of likelihood of occurrence of A union B. Therefore, these probability measures should add up. So this linearity property of the probability measure is what we would expect to be obeyed, and because of that we introduce another axiom wherein we say that probability of A union B is probability of A plus probability of B under the condition A intersection B is a null set. So these are three axioms that we come up with. Okay, there is no proof for these axioms. These are something which we start up with, we define it, and which is basically arrived at based on certain property that we expect this probability theory to have in order to model the real world phenomenons. And using these axioms we construct a theory, and then we check whether those theory make sense in making predictions. Okay, so this is what we say. So we lay out some axioms based on certain reasons so that the theory is logically correct, and then the theory is just pulled out of it, and therefore we call it as an axiomatic theory. Then one more certain other conditions or corollaries that can be arrived at based on these axioms are as follows. If A is a subset of B, then P of A has to be less than or equal to P of B, because there are certain sample points, okay, in B, out of which some of them are in A. So whenever a sample point corresponding to A occurs, then the event B has also occurred. So therefore occurrence of the event A implies occurrence of event B. Therefore the probability measure of A is less than or equal to probability of measure of B. Next, if you look at the set A minus B, which is the set of all elements in A but are not present in B, okay, then we can always express the set A minus B as A intersection B complement, because if you look at this Venn diagram, you have the set A here and B here. So B complement is everything that is outside B, and if you only include those which are in A and outside B, then that will correspond to the set A intersection B complement. Okay, so with this in idea, we can also arrive at one useful property. Let us say for an arbitrary set A and B, okay, A can be split into two subsets, A intersection B and A intersection B complement. So this is again shown here using another set D, but it's one of the same. A can be written as A intersection D. Here the symbol intersection is implicit, not being present. So A intersection D union A intersection D complement. So which is another way of telling that we divide the sample space into a two partition, D and D complement, such that D and D complement are disjoint but collectively exhaustive, and therefore A can be written as a union of this. That is, D and D complement is a two partition of sample space, because D and D complement are mutually disjoint but collectively exhaustive. So A can be written as A intersection sample space. The sample space can be written as D union D complement, and therefore A can be written as A intersection D union A intersection D complement, and so on. So if you replace B in place of D, so what we have here is A intersection B and A intersection B complement are two sets which whose union leads to A, but they are disjoint, and from axiom 2 we can see that P of A is equal to P of A intersection B plus P of A intersection B complement. Okay, because these two are disjoint sets. From that we can write P of A intersection B complement as P of A minus P of A intersection B. So this result we will keep using it in deriving some more laws. Then we can also see that in the axiomatic, while arriving at the sigma algebra, we forced that the sigma algebra should be closed under the set union and set complementation operation. This actually implies that the sigma algebra is also closed under set intersection operation or a finite number of intersection operations. This is what we will prove here. Let E1 and E2 be two events that are present in the sigma algebra F. Then following the closure property of the union, set union operation, E1 union E2 is also an element of F. Similarly, E1 complement and E2 complement should be an element of F because it is closed under set complementation. Therefore, the union of those complements should also be present element of F. So E1 complement union E2 complement is an element of F. And if you take a complement of this, again it should be an element of F. So E1 complement union E2 complement whole complement is an element of F. Now if you apply the De Morgan's law, you will get that E1 complement, one more complement, intersection E2 complement element of F, which means that E1 intersection E2 is an element of F. It can also be shown that if you insist that sigma algebra is closed under set intersection and set complementation, it automatically follows that sigma algebra will be closed under set union operation also. Well, now again we will come back to the discussions on some more corollaries that we can derive from the probability axioms. Let's look at the case of the A union B of two sets A and B which are not necessarily disjoint. Okay, if they are disjoint, their probability measures add up, but if they are not disjoint, then what happens to their probability measure? So we can see in this Venn diagram that the A union B can be divided into three regions. One is this region which is exclusive to A, which is shown using the horizontal dashes. Another region which is exclusive to B, which are shown using the slanted lines, and there is this A intersection B. So all these three regions are disjoint. So that is how we can split A union B. So A union B can be split into three partitions. A intersection B complement. What is that one? This region using the horizontal line is A intersection B complement, union A intersection B, union A complement intersection B, which is given by this region. And because these are all mutually disjoint, their probability measures add up. Therefore, it follows that P of A union B is P of A intersection B complement plus P of A intersection B plus P of A complement intersection B. Now, we can make use of the property that we have derived, that is P of A as we have shown here. Yeah, P of A intersection B complement is P of A minus P of A intersection B. Okay, what we are telling is this is P of A intersection B complement. You can get it by subtracting this, the probability measure of this intersection from P of A. Similarly, P of A complement intersection B is nothing but P of B minus P of A intersection B. So we can make use of these two idea, okay, to rewrite this as follows. P of A intersection B complement is P of A minus P of A intersection B. With this we will write it as it is, and then P of A complement intersection B is actually P of B minus P of A intersection B. Now if you look at in this one, this A intersection B, these two cancel each other, and therefore we have got P of A plus P of B minus P of A intersection B. Therefore we arrive at the one of the most important laws. P of A union B is P of A plus P of B minus P of A intersection B. Okay, then it also follows that in general P of A union B is all less than or equal to P of A plus P of B. Okay, because you see that this if you have a union of two sets, its probability measure, okay, is bounded. There is an upper bound on the probability measure of the union of two sets. It is the sum of the probabilities of the individual sets. So this gives a powerful upper bound if you have no idea of what the actual A intersection B is. Okay, so the equality will come when A and B are disjoint, in which case this probability measure of intersection B becomes 0. But this is a generic inequality that we can arrive at. Then let's consider three events A, B, C, which can in general be like this one. Then we can arrive at a law which will enable us to find what is the probability of A union B union C, which will allow us to generalize it to more number of union of more number of sets. So let's take A union B to be one set. You may call it as D or so if you want. So now actually P of this set A union B union C can be written as P of A union B plus P of C minus P of A union B intersection C. So again now we will expand this. This is PA plus P of B minus P of A intersection B plus P of C, and then this we can use the distributive property of intersection over union and write it as P of A intersection C union B intersection C. It follows from the distribution property. Then we can rewrite this equation as follows: PA plus PB. This is a shorthand notation. Sometimes we can write, instead of P of A, we can simply say PA plus PB. So this PA plus PB plus PC, we will pull it out here, minus P of A intersection B. And if you look at this one, again this is a union of two sets. Call it as X and Y. So it will be P of X plus P of Y minus P of X intersection Y. So we rewrite this whole thing in the square bracket as P of A intersection C plus P of B intersection C minus P of intersection of these two sets, A intersection C intersection B intersection C. And actually the order in which, if you do intersection, if there are more than one intersection, you can interchange the order. Okay, that is the associative property. So you will see that here it's nothing but A intersection B intersection C. So in essence we get PA plus PB plus PC minus PA intersection B, A intersection C minus B intersection C, but these two minuses together make the last term as plus. So this is a result that we can easily arrive. So it is easy to generalize this idea, okay, and arrive at the, for arbitrary set union of arbitrary number of sets in a sample space. Let a1 a2 to an be an arbitrary collection of sets in the sample space, and if you want to find probability of union of I varies from 1 to n ai, that can be written as sigma I varying from 1 to n p of ai minus sigma of p of ai intersection aj for ij lying between 1 and n. So we will take distinct pairs of ai and aj and find their intersection and find the probability measures. All such probability measures has to be subtracted, taken two at a time, but they have to be distinct. So that is why we have put forced I being less than j. So I and j can lie between, here you can see that I in general they lie between 1 and n, but j is always greater than I. So this makes that repeated pairs are not allowed, they are all distinct. Okay, so then taken 3 at a time, again we insist on the distinct triples. So 1 less than or equal to I, less than j, less than k, less than or equal to n. Such probability measures we add up. So the fourth one we have to subtract, the fifth one we have to add, and so on. So you will see that finally if there are n such things, minus 1 power n plus 1 p of a1 intersection a2 to all the way to an. Okay, we can see that it is actually minus 1 should come, because let us say when if it is if n is 1, that then we get p of a1 is equal to p of a1. If it is 2, then you would see that individual probabilities are being added, then the pairs are being subtracted, then if n is equal to 2, the final one minus of p of a intersection b comes. So this has to be a minus 1 power n plus 1. Okay, so this powerful law is called as the inclusion exclusion principle. So we include certain probability measures, then we exclude, then you include, and so on. So later we will make use of this property heavily, and then we can even define this sum as to be a sum S1, where this is a sum taken one at a time, this as S2, that is intersections of sets taken 2 at a time, and this as S3 taken 3 at a time, and so on. So this can be written as S1 minus S2 plus S3 minus S4, and so on. So you can see that in this sequence, this S1 will be larger than S2, because you see that these are all the same sets but taken 2 at a time, but we do a intersection operation, so therefore the sets will only get reduced and those probability measures are decremented. And again this will be lesser than this, because in addition to these, every such distinct pair will also be present here, but only thing is, in addition we will do one more intersection operation which will only reduce the probability measures, and so on. Okay, so here basically we are just, this S1 is a first approximation. To make it more accurate, we do a correction by subtracting S2. Okay, so this will actually overestimate this value. To do a correction, we will subtract S2, which is again an approximation. To get a better approximation, we will add the S3 term, and again another approximation is S4, which is subtracted, and so on. Okay, so which will also see that this factor S1, okay, is an overestimate for this. S1 minus S2 will underestimate this, because to this one we will, this is not being present. Okay, this addition is not being there, therefore together S1 minus S2 will underestimate. S1 minus S2 plus S3 will overestimate, and it goes like that. That will lead to a very interesting result, which will soon see that. This is nothing but the statement of the De Morgan's law, which we have already seen. Okay. Then we have an inequality called the Boole's inequality, which is stated as follows: P of A intersection B is always greater than or equal to 1 minus P of A complement minus P of B complement. In fact, there are two ways of stating this. P of A intersection B can also be written, this factor can also be written as in another way, as P of A plus P of B minus 1. So P of A intersection B is greater than or equal to P of A plus P of B minus 1. That is another form of Boole's inequality. We will prove this as follows. First, we will show that this and this are one and the same. There are two ways of writing the same expression. We will take this right hand side of this expression, 1 minus P of A complement minus P of B complement. We know that 1 minus P of A complement is nothing but P of A, and P of B complement can be written as 1 minus P of B, and therefore this is P of A minus of 1 minus P of B. So if you expand it, you will see that P of A plus P of B minus 1. Therefore these two are one and the same. Okay. Now we will prove this as follows. We know the well known result that P of A union B is equal to PA plus PB minus of PA intersection B. So this is the probability measure of a set A union B, which is a subset of the sample space, and therefore the probability measure has to be less than or equal to 1. This is true for any given set, including the set A union B. So this inequality can be rewritten as this. What we do, we take a 1 here, and that makes minus 1, and this we bring it to the right hand side, that will become plus P of A intersection B. An alternate way is as follows. We subtract minus 1 on both sides. So introduce minus 1 here as well as a minus 1 here. We add P of A intersection B on both sides. This gets cancelled while we have P of A intersection B here. Again, these two things get cancelled, which means that on this side you have got P of A intersection B, whereas here we have got PA plus PB minus 1. So this is what we started off proving, because you see that, so we have proved PA plus PB minus 1 is this is it's another form, is less than, this is greater than or equal to this or this. That is what P of A intersection B is greater than or equal to this value. So this is called as the Boole's inequality. Then there is the another inequality called as the Ben-Ferroni's inequality, which actually follows from our discussion on splitting the sequence of P of union of I varying from 1 to n AI into S1 minus S2 plus S3 and so on. So what this inequality tells is P of union of I varying from 1 to n of AI, that is union of an arbitrary collection of n sets, its probability measure of the union is always less than or equal to the sum of all the probability measure of individual sets. Okay, this should be very obvious, because here after making union you measure the probability measure, and that will be always less than adding up all the probability measures, and obviously they will become equal only when all AIs are disjoint. So this is nothing but telling that this value is less than or equal to S1, and we also saw that this will be greater than S1 minus S2. This is S1, that is taking the individual probabilities, and this is S2, probability measures of the pairwise intersection. So S1 minus S2. Okay. So we can go on further also, that this quantity will be less than or equal to S1 minus S2 plus S3, and this quantity will be greater than of S1 minus S2 plus S3 minus S4, and so on. We will create another law, generalize this law later. Then there is one more rule called as the implication rule. Let us consider a sequence of sets A1, A2, A3 and so on. Okay, they are all a sequence of non-decreasing events, in the sense that I is a superset of AI minus 1. That is, in other words, A1, A2, A3 are such that AN minus 1 is always a subset of AN. So they are, in some way, they are all, if you look at the Venn diagram corresponding to this statement, A1, A2, A3 are all sets such that they are expanding or non-decreasing. Okay. So let's look at such collection of non-decreasing sequence of events or sets in the sample space. Okay. So here you can see that AN is always a superset of AN minus 1. Okay. Then let us assume that in the limit n tends to infinity, this sequence converges to a set which we will call it as the set A. So what we know is that in the limit n tends to infinity, AN set converges to the set A. We also know that union of j varying from 1 to n, AN is equal to AN, because AN is the encompasses AN minus 1, AN minus 2 all the way up to A1. So if you make a union of all those sets up to n, that will only give rise to AN. So from that we can write down this formula, that is, if you take the limit n tends to infinity and take the probability measure of AN, it is equal to taking the probability measure of limit n tends to infinity AN. Okay, we can either take the limit as n tends to infinity of AN, okay, and then find its probability measure, or that will be nothing but the same when of the sequence of probability measures and take the limit n tends to infinity. So AN, and if you in the limit, this AN, okay, can also be written as union of j varying from 1 to infinity AJ, and if it converts to a particular set A, that will be the set A. So, and its probability measure of P. What we are simply telling is that the probability measures also has the same convergence as the convergence of sets into a particular set, as long as they are a non-decreasing sequence. We have a similar result for a sequence of sets which are non-increasing sequence of events. That is, you have got events, okay, A1, A2, A3, A1 being a larger set, a subset of that is A2, A3 is again a subset of A2, and so on, it goes like that, but it converges to a particular set A. Okay, then it can also be seen that in the limit n tends to infinity, AN, okay, will become A. Okay, either you take the limit of the set and then find it, this yields this, and then take probability measure, okay, or we can also see that intersection of n varying from 1 to infinity, AN will give you AN, and in the limit n tends to infinity, that becomes A. Okay, so this is again a result that can be easily seen. Now with this in mind, we will again go through the axioms of probability. we will stop at this point. We will have